Hello everyone, my name is Kais. My metric number is 226583 and I'm from group 6. So today is going to be about the definition of Laplace, and this kind of topic is really important because it's for the outcoming subject next year and you're going to really use it. So let me just share my slides. Okay. So going on with understanding Laplace. So this presentation is we explore the formula, the definition, and walk through a simple example. So what is Laplace transform? So Laplace transform is converting time domain into an S domain. So you have a function, any type of function, and you just want to um, integrate and transform it into an function. So it's simply just a transformation because it's simplify solving for ODE. It is widely used in various engineering fields. As I already said, it's really used in the upcoming subjects in the upcoming years. So now this is the formula of Laplace. It's when you're solving for an ft function, you just want to transform it to then fs, and fs formula is going to be 0 to infinity exponential minus st multiply the actual function that you have, and you integrate all this side. Now an ft represents the function in the time domain, and fs is transformation the function in the s domain. Okay, so what do you do here? You multiply, as I already said, you multiply by the function, then you integrate, and after integration, you just then it's transformation. So here's an example of Laplace of an function one. So I'm not gonna solve this. I'm just gonna go to the table, and because after this, I'm gonna do an example about this. So here you have this is common transformations for simple functions like e to the minus at and t1 sine at and cosine at. So a here is as a constant. You just plug in the values that you have. If you have like e to the exponential like power to the 2t, just change a and put let's say 2 here. So this is the use table. Whenever you're solving for the definition, you just use this table and just plug in the values. But I'm gonna solve now a question and go you through it so you could know how did we come up with this table. Now back with the example that I told you about. So I'm just gonna go walk you through this Laplace transform function. So you could know how did we get up with this transformation table? Because this is really essential to know the basics. So you could know how are we getting this specific function, transformation of function. So it's gonna be really simple. It does gonna include some use substitution method. So what are we doing here? We're just gonna apply the formula minus st multiply our function dt. Now we're combining both parts of exponential. It's going to be s minus a t. So it simply is just plus. It's just going to be adding, and then I took minus and t outside, so it came up with minus t is minus a. So it's just basics, nothing nothing hard in here. So next we're solving for u minus t, then du over dt is going to be just differentiate and then solve for dt. Dt is going to be 1 over du. Okay. So next we will plug in the values. We're taking this outside. It's a constant. So just take it outside. exponential to the power u du. Now we'll integrate. Now after integration, so the integration of e to the power u is just the same. So it's going to be 1 over s minus a. Okay, now we plug in the values that we had. Now we solved for u substitution, but now we plug in the values again because we already integrated. So it's going to be 1 over s minus a t. Okay, what are we doing here? Now we're just plugging in the values. Plugging the values, now we're starting with the infinity. So, this one, e multiply infinity is going to be minus infinity. This is just simple multiplication, nothing hectic in here. So e to the minus infinity minus e to the 0. Okay, so the exponential here, as we multiply to 0, anything that's power to 0, let's say 1 power 0 is 1, 2 power 0 is 1, is 1 as well. So now we know this as 1, and e to the minus infinity. This one is going to go also to 0 because it's the same as e in infinity, and 1 over infinity is just simply is going to be 0 because it's going to a really small numbers like 0, 0, 0 something. Okay, so 1 over s minus a, 0 minus 1. So 1 over a negative s minus a multiplied by minus 1. Okay, so the minus is gonna go away. So, and we're gonna end up with 1 over s minus a. That's actually the transformation for the exponential of a t. Now imagine this number is, let's say it's 2. So what are you gonna do? We're just gonna plug in the value here to 2, 1 over s minus 2. That's all you do. Now when you're solving for any type of functions, you have this transformation table, and now you know how did we come up with this transformation, and you should be good to go. Thank you so much. That's all.
Alaikum. Hello, my name is Muhammad Akmal Harit, and my part is explaining transformation for simple functions. I guess you guys already know the definition for a Laplace transform, which is this one right here. So let's start with our first simple function, which is a constant function. Basically, a function that is made up of just a constant. It can be whatever constant. It can be 5, 6, 7, 100, thousands, doesn't matter. But if you transform our constant function by using the definition right here, you will ultimately get this right here, constant divided by s, our new variable s. And this can happen provided that the real part of s needs to be bigger than 0. So that means our real part of s cannot be a negative number. And the Laplace transform is such. This is before transforming, and this is after transformation. The next up is ramp function. What is a ramp function? A ramp function is a function that is made up of just the variable. So for example, we have a function of time right here, and the variable is of course going to be the time itself. Transforming our ramp function right here will ultimately result in this right here, which is 1 divided by s to the power of 2. This is, of course, with the condition that the real part of s once again need to be bigger than 0. This is the transform pair. Okay, before transformation it's t, and after transformation it becomes 1 over s to the power of 2. For exponential function, right, for example, you have a function that is exponential to the power of kt. K right here is a constant, and t is, of course, our... oh my god, is my video lagging? Hello? Okay, sorry for that. Yeah, continuing. So if you have a function that is exponential to the power of kt, with k being constant and t is the time variable, it will result in this right here, 1 divided by s minus k. This is with the condition that the real part of our variable s needs to be bigger than our real part of k, which is the constant right here. And the transform pair is such as... Okay, continuing for sine and cosine functions. For sine function, which is sine of at, this a is constant. More specifically, it's a real constant. And also cos at for our cosine function. This can be derived using Euler's formula, which is this one right here, and the transform for for exponential to the power of kt, which we already get here. And so by setting k equals ja in the results of transformation of exponential to the power of kt right here, we will get this one. And of course, we don't want our imaginary number in the denominator, so we need to rationalize it by multiplying it with our conjugate, and so it will result in this right here. And this can be such given that our condition is the real part of s being bigger than 0. So this is equating imaginary and real part. Usually for transformation of simple functions, we already have a table provided because these simple functions are usually commonly found and is already been transformed for many and many times, and so people has already formulated a table for quick reference when you want to transform a function. Yeah, and that's it from me. Thank you so much.
So hello everyone, my name is Mohammed Bouzayan, my metric number is 226603, and I'm going to continue on with the basic Laplace with the idea of properties of Laplace transform. So there are three properties of Laplace transform. The first one is linearity property, then we have the first shift property, and finally the derivative of transform property. Those are the three different properties of Laplace, and I'm going to touch on every one of them very briefly. So starting off with the linearity property, which basically means that if you want to find the Laplace of f of t plus g of t, you can just find the Laplace of f of t alone, then add it to the Laplace of g of t. There's another idea which is if you have a constant times f of t, you can take the constant out, find the Laplace of f of t, then multiply it by that constant. So moving on to the second property, which is the first shift property. In the first shift property, you will have a function f of t which will have two functions inside. The first one is going to be the exponential, which in this case is the power a of t multiplied by another function which is the g of t. So what you have to do is you first take the Laplace, take g of t, find the Laplace of g of t, which in this case we're going to call g of s because it's a function of s from the function of time. And then after that, you look at the power of the exponential function and look at the constant that's multiplied by t. So in this case it's a, and then what you'll do is you'll take the Laplace that you found, right? Put it on the side, then you'll take what you'll do is you're gonna subtract this value, the value of a minus s. And then so it's going to be s minus a. So in this case, in this example, it's s minus 2. And then you substitute the s minus 2 that we got instead of the s in the Laplace function that we already found. So in this case, our final answer will be, for this example, 4 over s minus 2 squared plus 16. Moving on to the final property. The final property is the derivative of transform property. So in the derivative of transform property, you will have a function that's called g of t, which includes a power function, so t power something, times another function which we'll call f of t. And then if you have that sort of function, you can just apply the formula directly. The formula basically states that you'll take -1 times n. N is the power of t of the first function, not f of t, of the function multiplied by f of t. So t of n, you take the n value, it's going to be the power of -1, and then multiply it by the derivative so the order of the derivative in this case is based on the power of n. So in this example, for if we have here, we have to find the Laplace of t squared sine 2t, right? So we take the n as 2 because that's the power of t, and then because our power is 2 of t, it's 2, we are going to multiply the f of t, not the f of t, the Laplace of f of t, by by the second derivative, or by the order of the derivative of the n value that we have here. So in this case, it's going to be -1 power 2 because that's the n value, times the second derivative, because in this case our n value is 2, so the second derivative, times the f of s, so the Laplace of f of t. So here's a quick example that I'm just going to demonstrate with. In this example, I'll apply all the three properties that we learned. The first property is linearity, so we're gonna break it down into 3. So this is 1, 2, then third one. So starting off with the first Laplace, we have to find the Laplace of t sine 5t. So if you look at this function, you can tell that it's a derivative because we have a t value with the power, in this case is going to be 1. So our n value is going to be 1. And then you just apply the formula, so it's going to be -1 power 1 times the derivative, the first derivative, because d of n, so just the first derivative over d of s power 1 times the Laplace of sine 5t. So the Laplace of sine 5t, applying the rules that we learned in basic Laplace, is going to be a over s squared plus a squared. So it's going to be a 5 over s squared plus a squared, which is 25. You have to find the first derivative of 5 over s squared plus 25. So applying the quotient rule of the derivatives, our final answer, answer for the first one is going to be -1. We can keep the -1 till the end, it's not gonna affect anything else. So minus 10s over s squared plus 25 squared. And then moving on to the second one. So the second one we have is t times exponential power -3t. So what we can do is look at the a value. In this case, our a value is going to be the power of the exponential, the constant power of the exponential, so a is going to be -3. And then we keep this on the side, then we find the Laplace of g of t, which in this case our g of t value is t. The value of g of t is t, so g of s, also following the basic Laplace rules, is going to be 1 over s squared. and then we just substitute s minus a, so s minus 3, s plus 3 with this, so it's going to be 1 over s plus 3 squared. So for the final one is quite simple. We can just, the final one is negative 3t. The Laplace of negative 3t is basically negative 3 outside. The Laplace of t is similar to the one before it, is going to be 1 over s squared. And then we multiply this by negative 3. So our final answer for this one, not for the equation, but for the third one, is going to be negative 3 over s squared. And then now combining all of them together, our answer for this Laplace is going to be 10s over s squared plus 25 squared. We can remove this one because we don't need it anymore. Then we can just combine the other two, plus 1 over s plus 3 squared minus 3 over s squared. That is our answer for this Laplace transform. I hope you got the idea, and thank you very much.
All right. So, here I'll explaining about the inverse Laplace transform. So previously, we've known that the Laplace transform of ft is equals to fs. So the same way here, the inverse Laplace transform of fs is equals to ft. So a quick note: the Laplace transform only determines behavior of ft if the t is more or equal to 0. So same goes with the inverse Laplace transform. So to be more mathematically precise, we can write the inverse Laplace transform of fs equals to ft times ht. So what is ht actually? Ht is the Heaviside steps function, which is as written here. By multiplying ht, we are making sure that the function is 0 before t equals to 0. So this explains this whole thing where the t is equals to more or equal to 0. So the linearity property of Laplace is also applicable in inverse Laplace transform. Okay, so when solving a Laplace transform, it is important for us to know the table of Laplace transform by heart. So it's easier for us to solve Laplace transform or inverse Laplace transform question in the future. All right, so let's look at an example. All right, for the first example, find the inverse Laplace transform of fs when fs is given as 1 over s plus 3 times s plus 7. All right, for this example, it's quite simple. First, we have to solve it the partial fraction of this equation first. So, s plus 3, s plus 7 equals to, all right, 3. All right, so we have to find the a and b first by using partial fraction. So let me do the calculation real quick. All right, so after we've done the partial fraction, we'll get this equation: 1 over 4 times 1 over s plus 3 minus 1 over 4 times 1 over s plus 7. All right, so why do I write this like this? So I'll explain later. So now, from the table of Laplace transform, we know that Laplace transform of exponential a power of a times t is equals to 1 over s minus k. So from the previous partial fraction, all right, so we take this one, okay, because it is the same form as this. So 1 over s plus 3, where k equals to negative 3. So from here, we know that the actual function is e exponential of negative 3 times t. So same goes here with 1 over s plus 7, where 1 over s plus 7, where k equals to negative 7. Here, the actual function is equals to e negative 7 times t. So the Laplace inverse of fs is equals to exponential negative 3 times t minus exponential negative 7 times t. Alright, for the first example, find the inverse Laplace transform of fs when fs is given as 1 over s plus 3
inverse
times
Laplace
s plus
transform. So now I'll be explaining about the inversion using the first shift theorem. So now let's recap from previous lesson. So the first shift theorem, so fs is the Laplace transform of ft. So however, when ft is multiplied by the exponential a times t, the Laplace transform will be given as L e exponential a times t function ft equals to f s minus a. So note that the Laplace transform only works if the number s has a big enough real part, or we can write it as real number of s is more than sigma c plus real number of a. All right. So how do we use inverse using first shift theorem? So when expressed in inverse form, it can be written as L inverse Laplace f minus s a minus a equals to e exponential a times t times ft. Or we can also denote it as inverse Laplace of fs, s minus a equals to exponential a times t times ft. All right, so let's do a quick sample question.
All right, so here's a quick example of the inverse of Laplace transform using the first shift theory. All right, so here find inverse Laplace of 1 over s plus 2 power of 2. Okay, so first we have to remember that for first shift theorem, f s minus a, we can denote it as f s where s minus a. All right. So here, the equation is here. We can write it as 1 over s power of 2, where s is s plus 2. Okay. So from here, we can know that a here, all right, is equals to negative 2. All right. So since Laplace transform of t is equals to 1 over s power of 2, thus the inverse Laplace transform of 1 over s plus 2 power of 2 is t times exponential negative 2 times t. All right, that's all. All right, so here's a quick example of the
So
inverse
that's
of
all
Laplace
for
transform using
inverse
the
Laplace
first shift
transform. Thank
theory.
you.